Our next topic is going to be a simulationist guide to business analysis. We have Robert Churchill as our presenter for this topic, and I'm going to tell you about him. Robert P. Churchill has combined mechanical and software engineering skills to build and use continuous and discrete element computer simulation systems for nearly 30 years. He served in a vendor or consultant role in every life cycle phase in the fields of pulp and paper, nuclear power, document imaging, insurance, logistics, maintenance and reliability, and theme park operations. He's been a developer, architect, field engineer, data collector, technical writer, IV and V agent, manager, and analyst on desktop, network, web-based, microservice, and high-performance computing platforms. He has built real-time interactive and fire and forget systems for analysis, design, business operations, process improvement, industrial control, operations, research, and operator training. He is CBAP, PMP, CLSSBB, CSPO, CSM, and CSD certified. Please, let's welcome Robert Churchill.
Thank you, Julius. I think what all that means is I've done 80 different things and I'm not great at any of them. If any of you want to follow along on this, that is, I'll get to it. On my website, on the portfolio page under presentations, click on the title and it's that link will get you the slides. Alright, so in theory what we're talking about is the fact that doing simulation in order to be able to build and employ and do analysis with them, you have to really understand the system you're simulating. And it's the same thing BAs have to do. The next thing is that what BAs do is very varied. You've seen different one-ads. If you talk to each other, you often do very, very different things. There's a lot going on. I'll break that down for you. Mostly what I've learned is a kind of formal way of breaking down all the crazy things we do. But even though we've identified all these steps, there are still about a zillion ways to put them together. The main thing you need to know about me, if you guys remember back in the 80s, a guy named John Machida Jr.
Hi, Gene. How's the White House? Kids, how's the weather? How about those Yankees? I just got the proposal. I think the perfect way to proceed at this point, 10:30 a.m. would be for me to have my system duplicated, collated, translated, telegraphed, or reciprocated, reiterated, and exterminated. Then I think with all due haste, my system should tabulate word process and index and file it to make sure that every man in the child of the United States gets a copy.
Then there's Stephen Hawking. He doesn't talk that fast. So I plotted the talking speed on the Machida-Hawking scale. So that's down up at the top end. That is Stevie down at the bottom end. That's a young me wearing a horrible 80s jacket. And this is a new me. So my body is going in a Hawking-like direction. That's not good, but my brain, I think, particularly when it comes to business analysis, that's going in a Hawking-like direction, hopefully in a good way. So, like I said, I've been doing simulation for a long time. There are two major classes. Continuous simulations are based on differential equations integrated over time. They're about physical systems, and discrete event simulations are based on when events happen. The first one usually uses fixed time steps, like every quarter of a second, or every year if you're playing SimCity, or every zillionth of a second if you're simulating atomic nuclei. Alright, so there are a bunch of industries I've served in and a bunch of applications. Simulation is a broad a tool with a lot of applications. There are some major architectural considerations. I told you about the first one. The second one is interactive, where you do something and it changes its behavior in response as it's running. A video game will do that. A flight simulator, a nuclear power plant simulator all do that. Fire and forget is you hit the button, it goes away, does its thing, spits out answers, you analyze, off we go. Real time versus non-real time. One syncs to the same time we're in, again for trainers and whatnot, or industrial control. Non-real time, hopefully you're running faster. Just crunch it, dispatch it, you can go get it done. Single platform versus distributed, you either run something on one computer or have a whole bunch of computers put together. They all communicate, they all stay in sync, they all do different operations. And deterministic is where you hit the button, it comes up with a one answer. Stochastic is kind of like Monte Carlo. It generates some random point in the middle. You run it many times and you get a range of answers. So having seen that, done all these things, I saw a lot of different ways to approach problems, computer architecture, technical designs, and so on. So, why do business analysis activities look so different? If you all talk to each other, you might be figuring out what kind of server you want to use. You might be automating a process. You might be designing a new process. You might be figuring out why everyone hates the UI. They're all different. I've looked at a bunch of job ads. They all talk about different things. I've done a lot of surveys about 5 different groups, and what they say is interesting. They tell the story that, yeah, there are a lot of different things they do, and I'll try to make sense of that and explain why they're really all in a fairly uniform context. While we're at it, did anyone come up with some answers for the first section? Anyone want to volunteer and read them off?
So I did the stakeholder elicitation, brainstorming, requirements analysis, wireframing, and then process and flow diagrams.
Great. Those are all totally valid steps. everyone in the room that did it probably filled out something similar, but there are variations. How about anyone tell me what steps you took in a strange or non-standard project? Anyone? Something different, long-haired?
I created using Excel macro to go through and simulate the desired outcome of the process. Basically, then we were able to use for our QA of the system once we were able to go through.
Yep, that's kind of in the BAW, but not that way. So that's definitely long-haired. So if you're familiar with the BAW, there's an intro, some key concepts. The analogy here is roughly correspond to the phases of things you do in a project. They're kind of loose because there is no one set of things you do. Then it talks about competencies, then 50 techniques. I'll go into those. And then some perspectives. So one of the big perspectives I identify is the engagement versus the solution. So when I figured out, I was trying to make sense of everything BA doing all these different concepts. Everything I kept seeing, I watched a bunch of presentations, talked to a lot of people, did a lot of surveys. It all fit into my framework in a way. So I ended up calling it the Unified Theory of Business Analysis. So the framework, the way I do it, is basically plan it out, figure out what you're gonna use it for. And again, I did this based on my experience building simulations of all different kinds from beginning to end. And I found the same approach works for doing entire projects as a BA. Then figure out what assumptions you make, what you ignore, what you can get data on, the risks and impacts, and so on. The next step is the conceptual model, which is basically some representation of what exists, and I'll talk about that context. When it comes to requirements, that is sort of an abstract aspect of the to-be state. This is what we need. Hopefully it answers all the things above. Of course, we have the difference between functional and non-functional. Then we do the design, which is the detailed to-be state. Then we do the implementation. Then we test for both operation and usability and for outputs. And then we do the acceptance and closeout. So I plotted these phases against the knowledge areas, the 6 knowledge areas in the BAW. And what you'll see is it's kind of top to bottom, left to right, kind of the way it should be. The dark axes, or the highlighted ones, are the primary relationship, but there are secondary relationships also. And you can argue that any phase can be used during any step just about. So those are the 6 major phases, and the important thing to understand there is you don't do one, then another, then another. the important thing to make sure you're communicating with and getting feedback from your customer, either internal or external, is to keep going around till you agree. Then move to the next phase. Keep going around till you agree. If you find something you missed, go back and then keep doing this. And you can actually cycle through from any place to any place. You could also imagine several different teams doing all these activities at once. So if I'm doing waterfall, ideally, and we'll do that feedback and iteration, we just do them, right? If we're doing Agile or Scrum, we either have little sections in 2-week blocks, one after another, or we're kind of running a pipeline where things are offset and you're continually starting new things, working them through the pipeline, testing them and deploying them. If you're doing hybrid, you basically figure out what you need, then you can do the implementations in a Scrum-like or Agile way based on the order that provides value. Then you do a final integration test. And that's just one simple way to look at it. They obviously get way more varied and interesting than that. If we're doing a simulation, as I did many times, building the simulation is a project itself embedded in the larger project of whatever you're building the simulation for, either for training, control, analysis, or what have you. Also, if you're analyzing the existing project to find out what's going on, you do discovery data collection as part of the conceptual model to find out what currently exists. But if you're designing something new, right, you don't have that thing. So really this process is embedded in the design. I've seen some really interesting talks on different teaming concepts. I want to back up one bit. One of the major things I kind of identified in the BAW or BAW, as it were, was the difference between the engagement, which is that ongoing basic feedback process, and the solution, so figuring out what you need to build. So I saw this talk, and they talked about people who lead with their heart or their hands or their head, feelers, thinkers, and doers, and there are some hybrid roles between those. They all look, approach it from different aspects of the engagement. How are we going to do the process of doing our analysis? The SDLC cross-functional areas, by the way, if you're on my website, those are live links to blog articles. She defined 9 different rules, and you can see them there. And they basically talk about the non-functional requirements aspects of the solution. but they're still a little abstract. You can also define roles like what do people actually do, right? And they generally deal with the functional aspects of the solution. All right, here's a representation of a solution, or at least a process I want to analyze, or you do. And we have entries, exit, paths, entities that go through, stations or activities or process blocks, queues, parking lot. It's kind of a special queue that's not LIFO or LIFO. Things go in when they get there, they go out based on something else than when they got their order or something else. You can also have combined elements. So that's the engagement is, or the solution is about analyzing, automating, or improving that. Those are the parts. You look for commonalities between parts. I like to disaggregate things and find out, okay, what are the things that are the same? At what level of abstraction do I want to break them down? Now, one of the things that happens that makes your efforts look so different every time you do something, and every time different companies do things, and every time different individual VAs do, is you may only do a part of this. So in every effort, all that's going to happen, even if a lot of it is assumed away or kind of fluffed over, or even if it's a really big effort where everything is happening in a formal way, you only may be brought in to do a bit of it. Same thing with the solution. You might only look at what's going on in one box, or one pattern, one entity, or whatever. So I looked at the 50 techniques and tried to figure out whether they mostly address the engagement, which, or the solution, or both. Some are really general, like financial analysis and risk analysis, right? So they're very general. But a lot of things you do are only about the engagement, only about the process of solving the problem. Most of these techniques are actually about analyzing the problem itself. And maybe you think I should have broken these down differently. I'd love to hear feedback on it. Here's another thing. The survey asks people which tools they use most often. Most of the common ones that people use are more about the engagement, right? But some of them, and more technical tools, are about the solution. And whenever you get into Visio or programming languages or whatever, then they're about the solution. Statistical packages, that kind of thing. Another thing we worry about is not what it does, but what something is. If we're picking out a server or a vendor, it's not really a process. You're talking about its qualities, its features, and so on. All right, here are the actual phases of the engagement. I'll go through these kind of quick. Oh, by the way, what are some of your favorite software tools, and what did you write down? Don't know volunteer one.
We use Balsamic for mockups.
Okay, excellent. Anyone else?
Office.
Perfect. So we're doing planning, it's more of a PMBOK thing, PM thing, kind of standardized. It's bookended with a closeout step, and you can use any management technique you want. One of the interesting things I found out, going through many of the different bodies of knowledge and getting certified, all these things, is A, there's a lot of overlap, and B, if you go to the Wikipedia page, there's a section of criticisms for all of them. So none of these just say, do this and you'll get that, everything will be happy. You still have to add a lot of art and experience to the science. Maybe it's even a black art, who knows? The intended use, whatever you're going to do, has to be based on what people need. That was a specific term I got out of simulation. Assumptions is what you include and what you don't include. You try to figure out what has a major effect on things and what won't, and it's what you can reasonably omit and still get a good answer, and also the risks of having things go wrong. All right, the conceptual model, again, is basically the as-is state. Data sources only. All right. Data sources, you have to figure out where the data is coming from, where it's going, how it's transformed, what calculations are performed, what form it takes, the veracity of it, the obtainability of it, and so on. There are two kinds of data. There are data that describe the operation of different activities. So they're like adjectives which describe the noun. So I'll get to this in a bit. This was my confusion. Think parts of a process are the noun. So you find those out during discovery. You figure out what happened, what's there, where things go, what transformations happen, what entities go through the system or are processed by the system. Then once you know what everything is and what everything does, then you characterize it. So you basically do the adjectives. So that is, what color is it, how big is it, how long does it take, how many does it hold, and so on. Requirements functional requirements talk about what things do. That's pretty straightforward. Non-functional requirements talk about what things are. They're usually expressed in terms of abilities, right? Reliability, modularity, flexibility, robustness, maintainability, scalability, and usability. When I also lump in with there is how it's hosted and how it's maintained and governed. If you're giving someone a solution that is itself a process, you want to tell them how to run it once they have it, because eventually you might walk away depending on the nature of the relationship. So that is the to-be state in the abstract. What I mentioned down here, and I'll get to it in more detail, is all these phases should be tracked in a requirements traceability matrix. So everything should be linked to everything else going forward in the back, and there are a lot of ways to do that. The design is the concrete to-be state. That's what you're actually going to do in theory based on everything you've learned up to that point. BAs may or may not be part of that. They tend to support all the inputs to it and then be less involved with the actual implementation and design, depending on the situation. But they can be a deacon. Implementation is where you actually do whatever you're going to do. That includes transitions and includes deployment. You could, if you remember, when implementation and testing, we could also have a deployment and acceptance phase. So I wanted to keep that graph, that basic idea, fairly streamlined. Testing, you test whether the thing works. So verification is, does it do what you wanted it to do? Then you test the outputs, and that's validation. And that asks the question, or it answers the question, is what I needed to what was needed? Does it address or solve the problem? And understanding that distinction is important. Okay, RTM again, there may be a specialized tester, but BA should obviously know what's going on through all that. Acceptance, basically the customer, whoever it is, says either I accept it or I don't accept it, that was terrible, or I partially accept it, and you can go on and fix it, or we'll take it as is, or it won't go away. Hopefully you don't get the last two. Again, the middle part of the phase structure, figuring out what's going on, getting data, on improving your understanding of what's happening now, and addressing it is a cyclical process. Here, discovery is about the nouns and verbs. Data collection is the adjectives that describe those. So I've done both all over the place. There are a zillion ways to collect data. All right, process mapping. That one graphic solution that's essentially a generalized process map, right? You can include all kinds of stuff in it. There are a million kinds of maps. You can put in timing, you can put in state data, you can mix physical and informational things. As long as you come up with a standard representation that everyone understands, it's all good. So I've done this in different industries, a bunch of different ways. That was a turnkey mechanical pulping system. You basically dump wood chips, you steam them under pressure to soften them up. You run them through these mechanical refiners that are basically 5-foot plates with teeth on them that spin at high speed under pressure. They grind those things down into fiber. They jet them out, and that might be like a 22,000 horsepower motor. So they're big. Then you run it through a couple phases, separate out the steam, dump the pulp down into a chest, and then pump it out for further processing. One of the things that's on here is the state of the material that we're pumping. So it's like the flow rate, the consistency, which is how much paper to water, and the temperature. You can write down anything you want that makes sense for your situation. That is a off-gas system in a nuclear power plant. I did this early in my career. My God, did I learn a lot. Not a week goes by when I don't think of this model. I spent almost 3 years working on it, and I'm continually thinking, well, I could have done that better. I didn't understand that. It was fascinating. It was a whole career's education right there. That is a simulation of a land border crossing. So I was at 40 different ones in Canada, Mexico, the U.S., and on the Mexican border with Guatemala. We had a tool there that built simulations and then ran them. So think of that as that embedded project I showed you before. That one was just thinking about some generalized processes to figure out what standard components I needed to include in a generalized tool. Basically, every one of those boxes is a processor activity, right? This thing in the middle. And many things may be coming into it, and many things may go out of it. If you think about that going forward, like analyzing a process that already exists, it's cycle, right? Source, input, process, output, customer. But if you're going backwards, working from what's needed to what you have to put in, reverse it, copies, right? I learned that from some smart BAs in DC. It's not me bad. I think that's a really good insight for that concept. Not rocket science, just solid stuff. Again, I gave names to the basic components. Here's data collection. I wasn't looking for that slide. So here are the kinds of things you can get. One thing show up, how big they are, how many show up. If they leave one thing, how much goes here, how much goes there. Might be random, might be stochastic, might be deterministic. How long things take. There are a lot of ways to gather data. You can do it by computer. You could film something and then sit and count, write down when things got in, got out, how long they took, how many times they said, that would be tedious. I've done it. Calculations, photos, looking through documentation in that nuclear plant model. A lot of my discovery, you can't go walking around a running nuke plant and just measure stuff, right? You come out glowing green with 3 eyes. So you have to look at documents, drawings, technical data, and so on. That was my discovery. Actually, that was my data collection. They told me what the piping and process diagrams I had to model were. So that was the discovery. All that research I did, that was data collection to characterize it. Now, domain knowledge acquisition, this is learning what you need to know to operate in that field. So I've worked with external vendors a lot. One example was doing business process re-engineering based on document imaging. So instead of a company handling a zillion different physical documents and collating them and flipping them and analyzing them, losing them and carrying them around, they basically imaged them all, put them in a file, warehouse someplace, forgot about them, and then did everything electronically. And that saved like 30% of all the fiddling around they did. Really saved 40, so they added 10% to scan and index and saved 40% of the labor automated it away. But we did that for different industries. Insurance, banking, drug company, I don't know about that. My domain knowledge was in our tool on process analysis and so on, and mapping. And then what we had to do was know how to ask questions of the SMEs on the site, write down what they tell us, have them review the documentation so they know we got it right. So learning their process is domain knowledge acquisition. That's the requirement traceability matrix. The way this actually looks in practice, you can do this a million ways. There's a lot to it, especially if you have hundreds, if not thousands of different things you're tracking. But the basic concept is everything has to be mapped forwards and backwards. Some non-functional requirements will just start with requirements, or they may be driven by the intended use. And then how we do the engagement may also be part of the contract or what you've agreed to, so they're kind of their own thing. But the idea is, if you miss anything in this step, you go back and create something. make sure it's linked to some node until everything links in both directions. So I just wanted to show you what an example simulation might look like for a discrete event simulation. There are a lot of ways to represent these. You can make it look abstract. You can do it to scale. You can make nice graphics and look exactly like the thing you're simulating. You can generate down here at the bottom all the numbers you want about what happened. So again, this process I'm describing is if you do everything in detail, formally, and know you're doing it, you'll do all this. But if you and Bill say, you know, Ahmed down in shipping, he really hates that you go look at it. Or it's like, he's colorblind. Let's change the background to something high contrast. One change done. I mean, you do all the phases, right? But you're not going to go live and then kick off meetings and whatever. So all this stuff happens mentally or implicitly every time you do something. I described previously how these things flow in many different ways. One thing that's important is to find ways to be thorough. So I always like this book cover because it shows that if you look at something from a different angle, it may look totally different. Or you may be only capturing one aspect of whatever it is or whatever is going on. So there are some formal ways to try to get you to be thorough. UML is one, so that looks at things from the point of view of how things are hosted, what gets processed, the users, everything else. Sometimes you can do a formal mathematical proof, sometimes you can't. In the end, if the customer is happy and they get the results they want, that is the ultimate judgment of whether you succeed. One of the inspirations for this framework was this crazy spec written up by the Navy. And the PhD did it. This guy was 12 kinds of a character, really hard to talk to. I ended up adopting or fitting in things from books and this and whatever. So he basically said, embed whatever you do in a B&B plan and accreditation plan. So let's say we have something we're doing that's in the middle, everything we do. We want to plan for and then prove what we did to do B&B. And similarly, maybe this is from the customers or even a separate third party plan to look at all the same thing from the point of view of actually accepting and accrediting. So I've simplified that. And that guy was nuts. Process improvement. Again, that's taking something you already have, making it better. question is whether you're gonna figure out some little thing to make it a little better, or go for the big kill and make something a lot better. Some ways you can do that, or rearranging everything, just something that's more a lean way to go. Improving quality is reducing variation, that's a Six Sigma way to go. You can modify individual parts. You can overcome constraints. A lot to do there. For those of you who don't know Monte Carlo analysis, imagine driving to work and imagine all the crazy things that can change. Now, most days, maybe it takes 25 minutes, right? But some days it may take an hour and a half. And if you go in Saturday morning, maybe get there in 15, hit all the green lights and no potholes, your car doesn't break down, there are no school buses, zip. But if your neighbor pulls out in front of you, some guy with a boat trailer is poking along at 8 miles an hour, and get behind him, there's a wreck, and so on. So if you assimilate or gather data on the possibility of all those things happening, run this simulation as you do in your life, a whole bunch of times, you get a cloud of potential outcomes. And the way you usually manage things like that, you can't really prevent everything bad from going on. But you set up a KPI that says, all right, 80% of the time I want to get there in 25 minutes, and that's good. Those are just some examples of how you generate random data, right? Those are kind of standard die rolls. There's a bunch of different combinations, but in reality, you collect the data based on what actually happened. And a lot of things like in inspections, or most of the results are clustered in a small number of ranges of possibilities in one area, and a long tail where things go really wrong or take a long time. So organizations essentially exist to provide value. BAs are all about trying to do all the parts to analyze how we do that. What do people mean? What's it worth? Again, Wikipedia has a criticism for everything. As I said before, there are no silver bullets. There's no cookie cutter response. You just have to do it over and over again until you get comfortable with it. There's a really good book called Facts and Fallacies of Software Engineering. And it says that every time somebody comes up with something new, they think it's going to change the world, but nothing ever does. So it makes a quantum change in some area that is really applicable to object-oriented programming, for example. Really good for simulations, user interfaces, maybe containers, a lot of other things it doesn't help, right? So everything like moves the industry another day of time. And this has been happening for 50 or 60 years. So every time you see something new come down the pipe, it's not going to change everything. It's just going to make things a little better. So we talked about how simulation works, practice of doing what it is we do. We talked about why the BAW is kind of vague and unstructured because the work we do is that way. We have to be adaptable. Hopefully the unified theorem shows you the context of how all these pieces fit together. And that is it. Thank you.